Greetings everyone. Today I'd like to present the research about computational cost reduction of transaction signing in blockchain. My name is Geetikul Suksomsathan, the first author from University of Phayao, Thailand. The co-authors are Associate Professor Dr. Ian Welch, Assistant Professor Dr. Sakorn Meglasawanit, and Dr. Jirasima Sihiran. I graduated Master of Science in Computer Science. For my working experience, I have been working for Department of Computer Science, Faculty of Information and Communication Technology, University of Phayao as a lecturer for about 15 years. I'm currently studying a PhD in School of Engineering and Computer Science, Victoria University of Wellington, New Zealand. My area of interests are full stack Python, cybersecurity, cryptography, and blockchain. This is an abstract of the paper. I will skip this because it's quite wordy, so you may pause the video if you like to read it all. Some of you may know about blockchain, but some don't, so let me show you real quick what the blockchain is in practical on the web-based simulation I have been implementing. So let me introduce to you what blockchain is on web-based simulation. Typically, we use SHA-256 standard hash in blockchain, and the hash is regarded as the digital fingerprint of data because you may notice here is empty data and here is a hash of the empty data. If you want to add a number here, you will notice that hash will change as well, and I want to type my name. So this is my name and this is the digital fingerprint or hash of my name. So if you add some character, the hash will change. Even you add some space, the hash will change. Technically, the hash is made of not only the data, but also the block number and the nonce as well. The nonce is random number used only once. Now the block is green, which means you have the suitable nonce for the block number and the empty data. If someone try to change any pieces of data, block number, nonce, or data here, the block will turn red, which means it's malicious. So if someone change the data, you have to mine it again like this. Previously, I explained to you what the block is, and this is the chain. The chain is the hash of the previous block. This is the hash of this block, and this is the hash of the previous block, which is exactly the same of this number. That makes you understand that which block comes first and which block comes second makes the order and the link of the blockchain. So if someone wants to make modification by adding number, the hash will change, and what you have to do is mine it again to find a suitable hash. Not only this one that you have to mine it, but the rest of them as well. That makes almost impossible for the malicious person to change the data. So the previous example is about one computer in the network, but in reality there are more than one computer, and if someone tries to change data, the hash here will be different from the rest of them. In which block number 2, that makes the system know that in tier A someone changed data. The rest of them will not approve because it's called consensus. If you want to approve your data to the rest of the computer in the network, you have to have more than 50% of entire network to have your block approved. So how it works? Assume that Alice wants to send the cryptocurrency to Bob like this, but Mel wants to change the amount of money. So how are we supposed to do? There are 6 steps. Step 1, Alice wants to send the money to Bob. Step 2, the transaction is represented online as a block locked by the key. Step 3, the block is broadcasted to every computer in the network. Step 4, the network approves the transaction. Step 5, the block is added to the end of the blockchain. Finally, the transaction is completed. So our contribution is about step number 2. So let me show you how the key works in the video I previously recorded. This is a basic concept for creating public and private key pairs in blockchain. First of all, I will type my private key, which is kept in secret 2021. So this is a public key generated using the RSA cryptographic algorithm in 512 fixed length hexadecimal numbers, or you can click random here. So I like this number 9907. So and this this is public key, which is gonna be the digital wallet address. This part is about signing and verifying transactions in blockchain. We want two pieces of data to make the message signature. For example, $100. The private key is from the previous step. The sign want to generate the message signature using the cryptographic algorithm. So Alice just signed message here using her private key. Once Alice has message signature, she sends it to Bob, and Bob gets the signature, the message, and Alice's public key. Then Bob has to verify without Alice's private key. So if the message, the public key, and the signature are identical, the verification will be successful like this. This part is about signing transaction as well, but more practically. So this is Alice's message, and this is Alice's private key, and this is Bob's private key. This is Alice's private key to sign. So this is a message signature. After signing, the message will be sent to Bob. Bob get the message and the signature, Alice's private key and his private key. He wants to verify using just Alice's and his private key. Then click verify. So this transaction verification successful. But if someone wants to even change 1 cent like this and verify again, the message is modified, so verification fails. So our research goals are: number 1, to develop the protocol that can reduce the complexity and mathematical costs in signing and verifying blockchain transactions. Number 2, to analyze the performance of our protocol measured and visualized by Python. So we run the experiment 10,000 transactions with 512-digit public key with 5 and 512 private key. Then we set up our security model for signing on the left-hand side and verifying on the right-hand side. For the arithmetic transformation, we reformulate the legendary symbol to Euler criterion, then reduce the length of the key using extended Euclidean algorithm, then factor of 2 from them using the law of quadratic reciprocity as following. The first result shows that if the private key is very small, which is 5 digits, our scheme is almost on the x-axis, which is lower than 10 milliseconds, compared to the legendary symbol about 15 seconds and the original one 60 seconds at 512 digits of the private keys. This is a close-up of previous graph of our protocol. The time taken around 50 to 90 milliseconds. This is the second result when the private key is large, which is 512 digits. The graph illustrates that the protocol consumes as many time as our previous one at approximately 10 seconds. However, our protocol's runtime is still cheaper than the rest of them, which is about 6 times lesser than the original one. Moreover, it tends to have more differences if the key is getting bigger. In conclusion, the findings from the analysis of both small and larger key size of the private keys shows that the runtime consumed by our algorithm is very impact. Moreover, it is supposed to significantly reduce much more time on signing and verifying in practical blockchain. Therefore, our contribution on computational cost reduction of transaction signing in blockchain is beautifully successful. Thank you for your attention. Any comments, any questions, please don't hesitate to email me. Cheers.